So
Okay. How's everybody today? How are you today?
Alhamdulillah.
Good. So let's continue our class with I promised last time to give you more space to ask question or more opportunity to ask question on BJT. Is there any question on BJT?
Madam, can you explain the cut effect again? Because I don't understand it.
Ask me specific question, more specific than that.
Okay.
Okay. You are thinking?
Okay, so when the
Yes.
why does the base region need to be wider? Like
Because the what they call the active base region is wider. The base region remains the same. However, the base region consists of the depletion region and also the active region of the base. The active region of the base where the recombination occurs. Recombination doesn't occur in the depletion region because there's no free carriers over there, right? So when the depletion region changes, therefore the active region of the base also changes. So the depletion region becomes smaller, hence the active region of the base become bigger.
okay. Okay.
All right. Any other question? From the floor? No?
Hello, test.
Yes, Aiman, what's wrong with your camera? Cannot see your face.
I'm not sure. I'm around here. So the question is, in ideal, why IC remaining constant when we increase the VEC?
Can you repeat that again?
Why IC remain constant when we increase VEC?
VCED? VCED? What do you mean by VCED?
VEC.
VEC?
Yeah.
It is in what context you're asking?
Ideal.
Okay. Because so why the beta remains constant? Your question, right?
Yes. Yep.
Because the base current will also increase accordingly. Dia berproportionate, dia akan increase, sama increase. So when both are increased in the same rate, the beta will not change because beta is just the ratio between IC and IB. Do you get that or no, Aiman? Ask me question if you don't ask, you still don't understand.
You mean the base current is the recombination process or something?
Okay, good question. Then I will ask you again, how do you get base current?
Through recombination at P.
Yes, so does that answer your own question?
Okay. What if the reverse bias becomes more steeper?
It's the same when you what happens when you increase the reverse bias further, right?
Yes.
Okay, so in that case, normally let me So normally in a circuit, right? You don't if you still remember your first year, do you define as a BBC or VCE? Oh, right, do you understand? So because when we bias the circuit, normally we bias the circuit with respect to the emitter, right? Aiman?
Yeah.
Yeah. So always VCE, BBE. So we always with respect to the emitter side. Therefore, when the condition you are saying, you increase reverse bias without changing the emitter. Is that your question?
Yes.
Yes.
We just increase the reverse bias.
Right. So normally it doesn't happen in normal circuit lah. Okay, because all the circuit, if all situation normally we respect to the emitter, but normally kita buat macam tu because the circuit will be complicated to have two different circuits. So normally we return it back to the emitter. But let's say the hypothetical your condition occurs, right? So you tell me, if you increase BBC without changing the emitter, what will happen?
The IC increase maybe because drift. We change the VBC, which means we increase the reverse bias voltage.
Yeah, that was your question, right?
Yeah. So basically the more current will be collected at C.
What is current?
The electron.
What is current?
What is current?
What is the definition of current?
Net flow of carrier per unit time.
Okay, good. So therefore, okay, with that definition, and you increase the BBC, can you think again? What happens? So when you say the current will increase, is that correct? Will the number of electrons increases?
No,
Why not?
because we just increase the voltage, not the doping.
Where are the carriers coming before it being collected at the collector? Where are the carriers coming?
Emitter.
Yes. So if you don't change the emitter current or the voltage, will that change the number of free carriers that goes into the collector region?
No.
So that answers your question, right?
Yeah, all right.
Okay. Any more question? So that's called critical thinking, answering question with question. Instead of I'm giving you the answer, I will give you more question for you to think. So then you get the answer yourself.
Madam, one more question.
Okay.
At early effect, what does it at early effect?
Early effect, okay.
Okay. What does it mean by higher dN over dS?
It means that what is the n over the x?
Slope.
So of what?
Slope of I'm not sure.
Okay,
I just think the slope.
so that's the first question you should ask me, right? So what's the difference? What does it mean higher? So I'm just teaching you how to ask questions. So when you ask a question, you should always go to the root of a question. Then you build from there. So you don't know. Anybody here knows what's the n over the x? If you don't know, why didn't you ask before? That's my question. You don't care to ask. The n over the x. What is n? What is n? Normally in semiconductor, what is n? Tell me. Mm.
It's number.
And is what?
Number.
Number of what?
Free moving carrier.
Which free carrier?
Electrons.
Yeah, of course. Why do so? This is very basic, right? Everybody should know. N is the number of the concentration of free electrons, right? So P is the number of concentration of free holes. So dn over dx. What is x? You think? Ahmad Gharib, what is x? Ahmad Gharib, you done?
Yes, madam, I'm here.
What's x? You think?
Could it be the distance?
Distance. Good. So what is dn over dx, Ahmad? This is mathematics, but translating it into physics. What's dn over dx?
Well, how would I explain it to physics form? I would say the amount of electron over distance. Is that correct? Or the flow of electron over a specific distance?
So yes, but you have d over there, right? If n over x,
Derivative?
there's a ratio, right? Of dn over dx. It means maths that you learn is
dn over
is the
dx.
gradient, the rate of change, right?
Yes.
If you still remember,
So the change of the change of electron over a period of over a distance, right?
yes. So the change of
Yes.
the number of free electrons per unit distance, per distance. So therefore, that's why they panggil, that's why it's called concentration gradient. So if you still remember that this is taught before, when we talk about diffusion, we talk about concentration gradient. Okay, so when there's a concentration gradient, what will happen? Diffusion will happen, right? Diffusion will happen. So what's your question again? Apa nama ni? Aiman?
What does it mean by higher dn over dx?
Kat mana? Shorter effective base width. So basically the gradient becomes higher. Basically is a nut. As I mentioned dalam slide ni, perkataan dia payah-payah. That's why you need to read textbook as well. So what it means is when you have a shorter effective base width, you can say in terms of higher dn over dx, or another way of saying it, which is easier, is you will make the base distance to the effective base distance shorter. Therefore, what happens to the recombination? When the effective base width becomes shorter, what happens to the recombination, Aiman?
It will become less recombination.
Good. So when it becomes, you have less recombination, then what happens?
So yep. So more current will be drift to N. More electron will be drift to N. And type at collector.
Okay, because emitter also N type, you know. So
Yeah.
So need to be careful in the exam if you say something. Yeah, so because IC equals to IE minus IB, right? So the carriers which are not recombined will go to be collected at IC. Okay, carriers which are not recombined will be collected at IC. So if IB is reduced, therefore IC will increase. So that's why as you increase VCE, you will see the IC increases with VCE. Okay, because the base current reduces due to the early effect. Okay, does that answer your question, Aiman?
Yes. So basically, we just the early effect, we increase the depletion region, so the recombination decrease.
Yeah, it's like nearly the opposite of Kerr effect. But Kerr effect, how the N is the opposite, but how the physics why early and Kerr effect happens is totally different. So you need to understand the physics of the two. All right.
Okay.
Any more question on BJT? If not, I will go to the next what you call it, topic, which is Mosfet. Calling once, calling twice, gone. Okay, so I expect you fully understand BJT because you didn't ask me a question on BJT. Right, so next we'll go through Mosfet. What can you see? What about it? Can you see Mosfet? Can you see the
Yes,
Mosfet?
madam.
Okay. So next is next of the semiconductor device that you'll be learning is Mosfet. Mosfet stands for metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor. So from the name, you understand the structure of the Mosfet and you understand how it works. Okay. So although Mosfet is also a transistor, but how it works, the physics of Mosfet is totally different as compared to the BJT. But both in the end have similar application. For amplifier, can become a switch. But how it works, the physics of it are very different. So these are some history. You can read it on your own. BJT was found first. Then after that, they discovered Mosfet. However, at the end, Mosfet wins because nowadays everything, your integrated chip, all the electronics are mostly using Mosfet instead of BJT. The reason being because one of the main reason is you can make Mosfet very, very small. BJT have a limitation to make it small. Plus, it's about like competition between research between Mosfet and BJT. So when many research has been done on Mosfet, so Mosfet are more advanced. It's easier to control and to make Mosfet. So that's why Mosfet wins. Okay, in the end, right? So, but Mosfet, one of the main reason why Mosfet are the chosen transistor is because we can make it very, very small. Okay, without jeopardizing how it works, the physics of it. So most of the VLSI, you learn that we'll be using Mosfet. So okay, Mosfet can be used both in the digital and analog, similar to BJT. Okay, it can work as an amplifier. It can also work as a like switch on off digital. So the difference is how it works. BJT, bipolar junction transistor, the name bipolar junction transistor. Junction, is a PN junction. So bipolar, is using two different type of free carrier for the current inside BJT. In Mosfet, it is easier in the sense that there's only one type of carrier that contributes to the current inside the Mosfet. So how does it work? We'll go through after this. Okay. Right, so I will start drawing. So now it's another type of transistor called Mosfet. So from the name, we can draw the structure. So you should be able to draw the structure in the exam or quizzes or assessment. So the name metal oxide semiconductor. So we start with the metal. So you have a piece of metal, then you have the oxide layer. And then you have the semiconductor layer. Okay, so from the name comes the structure metal, oxide, and semiconductor. So what is the oxide? Oxide is a type of insulator. Insulator. So if you are using silicon, for example, so let's say this MOSFET are made of silicon. MOSFET can be made of different material, can be from gallium arsenide, gallium nitride, all the other semiconductor materials. But the one that been using in your, what do you call it, in the integrated chip and most of the electronics are made of silicon because it's the cheapest. You can just purify sand to get silicon. So sand is actually silicon dioxide. Sand is a silicon being oxidized, silicon dioxide. So if you remove the oxygen, you are left with pure silicon. So if it's why another thing, this is very convenient for the design or the manufacturing of the MOSFET is that this oxide insulator is just silicon dioxide. So because silicon dioxide, the sand that you go to the beach is actually an insulator. So you just put metal, you put the silicon dioxide over here, and then the purified silicon. Silicon. Then you get the structure of metal oxide semiconductor. Now, let's see how it works. Before we talk about how the MOSFET works, let's learn about the name is MOSFET. So MOSFET here is metal oxide semiconductor. What is FET? This is field effect transistor. Field effect transistor. So we need to understand what does field effect means. Field effect is the physics of how the MOSFET works. Okay. Now, let's say saya draw silicon besar sikit so that senang nampak. Okay. Let's say I apply a voltage at the metal side. Okay. If I apply a voltage at this metal, I apply a positive voltage. What will happen in this structure? Okay, I'm applying a positive voltage to the metal here. What happens to the free carriers in the silicon semiconductor? Anybody wants to try? Okay, let's try to make it easier for you. Let's make the silicon p-type. So this is silicon but doped, p-doped p-type. So what will happen to the carriers inside the silicon semiconductor?
Repel, madam.
Huh?
Repel. The holes repel.
The holes will repair from where?
From the top to the bottom.
Okay, good. So because here you have the majority carriers are the hole, right? So majority free carriers are the hole. So because of the positive voltage that you apply over here, there's a field effect across the insulator because carriers cannot travel through insulator. But what happens is it can create a field, electric field across the insulator. It's similar like a capacitor. So if you learn capacitor in your A level for SPM, you have field effect inside the capacitor in the insulator between the two plates. So what happens is, yes, correct. So Amy was saying the hole are being repelled. What else happens?
The electrons are attracted to the top.
Good. The electron is a majority or minority?
Minority.
Good. So the minority electron now will be attracted to go to the surface or the what's the word that I use? Go to the surface between the semiconductor and the oxide layer. So because these electrons cannot go beyond because of this insulator. So what happens, dia akan kumpul lah. they will be accumulated over here. Okay, so this is called field effect. This is called field effect. By applying a voltage over here, you are inducing a field inside the insulator, or therefore then you will separate the carriers inside the semiconductor. Good. Let me change this again, just to test your understanding. So if I change this to silicon N-type, and I change this to negative voltage, I connect it to negative voltage. What happens inside the semiconductor? Rahimi?
Electron will go downward
Hmm?
and minority of holes will go upward.
Good. So the electron will repel. The word is repel. The electron will be repelled from the junction or the surface or the junction between the insulator and the semiconductor, while the hole will be attracted. The word repel and attract. So why the minority of hole will be attracted to go there. Good. Okay, now you understand the principle of field effect transistor. Now we want to understand how do we get current inside a Mosfet. Okay, so now it's the same thing except for now I'm drawing the semiconductor bigger. Okay. Now, not only that, so this whole piece is a semiconductor, but now I dope it slightly different. Okay, so this whole piece is semiconductor, but the way I dope it, I will have a region, two region. So I have three region in the semiconductor, 1, 2, 3. Okay, so this region over here, and the region over here, I dope it with, let's say, N-dope, N-type. This is also N-type, and this is P-type. Okay, it's a still piece of same semiconductor, but now I dope it slightly different. So I dope it this N-type, this N-type, and then this become the P-type. Okay, then I connect this. I make a metal contact, and I connect it to the battery or to the voltage. So what happens is I can connect this and make. So I have three terminals now. I have the source, I have the gate, I have the drain. Okay. So now, if I apply, now I'm applying a positive voltage at the gate. What will happen in my semiconductor? Faris?
The whole at the p-type will refer to the downward,
Okay, good.
and
Then,
minority at the p-type, minority electron at the p-type will
be attracted.
connected at the top.
Okay, so the hole will be repelled away. And most of the time we don't draw this hole because it's not important to the what you call it, the physics of Mosfet. So biasa kita tak draw, we don't draw this. We just draw the minority carriers because the minority carriers are the one later that will give rise to the current inside Mosfet. So let's draw just the electron. So the electron will be attracted, right, to here, to the surface between the insulator and the insulator and the semiconductor. Okay, so now this happens. Okay, so before that, okay, before we talk about this, kita reverse sikit. If this is a MOSFET, right, will there be current flowing here? Do you think if I don't apply any voltage here? I apply a voltage here, so I ground the source and I apply a positive voltage at the drain. Will there be current flowing in my MOSFET if this is the situation? My Sarah? My Sarah, you there?
My answer is
Hmm?
no,
Why not?
because grounded, so
Huh?
no voltage supply, so there is no movement of.
No, we apply a voltage here, positive voltage here. Will there be current? My Sarah?
Not sure, madam.
Pink.
Yes,
Why? How?
because there is a flow of electron from N to P, P to N. I'm not sure.
Now think about it. Which P to M? I want you to think.
When it is connected with the voltage, the electron from N will diffuse to P, and
Which N here? There are many N here. They hand at the source.
the N that connected with drain.
So this N, okay, then
The electron from that N
huh?
will diffuse to P type,
Then
and the holes from the P type will diffuse to the N at D.
but
I'm
the
not sure whether.
but the P here is not connected anywhere, right?
Oh yeah.
Then how is it? How what?
But
How
current means there is a flow of electron. Free
Yeah.
electron.
There must be a flow of electron. Therefore, there must be kalau this is connected to voltage, there's be another side that will connect it to the circuit, right? So then current can flow. But ni tak ada satu. So there's no di nak pergi mana current tu?
So the answer is no current.
Can you see two diodes over here? Anybody can see two diodes? Where are the diodes? Huh? Aku tanya Kamalia, can you see the two diodes over here?
Not sure, madam.
See with your basir, with your mata hati. See. Can you see two diodes over here? Kamalia, try to see again.
No.
So telah buta. You don't see. You are blind. So let's see. Let's ask Ikram. What do you think? Can you see two diodes over here? Ikram?
No, madam.
Kau pun blind. Are you sure? Kita dah belajar bersungguh-sungguh PN junction. Diode. I give you one more chance, Ikram.
Yes, madam.
Huh?
Yes.
Kat mana? Where is it?
The contact of P type and N type.
The contact? What do you mean by the contact?
P type contact with N.
You want to say junction?
Yes.
Junction is better, right? PN junction. Bukan PN contact kita panggil dia kan.
Junction.
So the junction between P and N over here. So this is one. So where's the other one?
On the right side.
Okay. So, okay, thank you. So here is the two PN. So with the structure itself, I don't have to tell you there's a diode. You know when the P and N meet, there's a junction. So there automatically there's a diode over there. So this diode is, and this whole thing over here. Macam tidak sensitif. Okay, so these two diode. The battery. Let me charge for a while. My was the pencil. So So there are two diodes over here, and you can see the diode. The P of the diode are both of the P of the diodes are connected, right? Yes or no? Is the two diode connected or no?
Yes.
Yes. How is it connected, Kamalia?
Um, the junction. Oh, and the source. The
The what?
the voltage.
Okay, let's remove the voltage here. Tak ada voltage lah. There's aku confused on voltage tu. Interesting. Kau sebab hari tu jatuh. It doesn't want to. I'm going to prepare baru. Okay, so there's no voltage here. So what is the two diode connected or no, Kamalia?
Yes, because there is the NP junction, PN junction,
What junction?
PN junction.
How the diode is connected?
The
How is the diode connected?
because there is a flow of the diffusion and the drift of the free carrier.
No. Ikram siapa lagi yang saya tak tanya lagi? Let's see. Who's Islam? What do you think? Is the diode connected or no?
You see here in N type, there's no voltage.
No voltage at the end and at the end type. So is the P is the diode connected or no? My question. Huh? Islam?
It's not connected.
Not connected?
Yes.
I cannot hear you. Can you say it again?
I think it's not connected.
I think you need to remove your hand from your mouth. It makes it not clear. So when you, or because you're holding the microphone, okay, it's okay. Because I cannot see your mouth when you speak, so it's make me more difficult to understand. So again, is it connected or no?
Connected?
Huh?
It's not connected?
So you say it's not connected. Let's ask Elmi, what do you think? Elmi, you there?
Test.
Mm.
I think it's connected
How?
because they share the same P semiconductor material.
Yes, good. So the answer is it's connected because both are this pen. So interesting data. So because they both of these diode. I understand kenapa dia. Because of the two diodes shares the same P. So because diode is just P and junction, right? This whole P are all the same P. So it means that I can draw schematically that the diode looks like this. Okay, so the diode are connected. So if you see here, if I redraw this again, what does it mean? Ikram, this. What does it mean? Can current flow? Ikram?
Wait, wait.
Huh? Can current flow, no?
Yes.
MashaAllah. Yes, how? Maybe it's a miracle that will happen. How the current will flow? Tahu dah salah. So, so how is it possible, brother? This is PN junction diode back to back. Diode is only allowing one direction of current, right? So dia pergi sini tak boleh, pergi kat sini tak boleh. So if you have a back to back diode like this, definitely there's no current. Current cannot flow because either side because in order for current to flow, you need to go from one side to another side, right? But here this way cannot go, this way cannot go, so therefore there's no, it's not possible for current to happen. That's why another thing, a good thing about MOSFET, the leakage current will be very small because when it's off, it's naturally, the structure is naturally back to back diode. When you're off, let's say if you have a handphone, right? When you off your handphone, do you want it to use the charge or the battery? No, right? You want to save it. You want it to, like, what do you call it? The battery will last forever if you off it off. So it means that but in real life, if you don't turn on your handphone, right? You off your handphone. After like 1 month, is there any more charge in your battery? Huh? Answer me. Faris, answer me.
Lesser. The battery lesser than before.
Yes, lesser than before, and one time will be 0, right? Why? You off the phone.
Because the leakage.
Because there's this leakage current. So leakage current is another, what do you call it, another secondary effect of MOSFET. So now I'm teaching here is the ideal of a MOSFET. Ideal MOSFET, ideally this is back-to-back diode, impossible for current to flow. However, diode is also not ideal. So if you remember, we will talk about diode, right? We will talk about diode. Diode have a reverse bias. Reverse bias supposed to be 0 volt, right? 0 current, right? You shouldn't have any current in reverse bias of a diode. But when we draw the IV, the current voltage, you will see that in the reverse there's a very small current, maybe picoampere, 10 to power minus 12 amp of current. So in ideal world there is still current. Why? You have generation recombination of the minority carriers. That's why you get the saturation current. So the same, because the physics are the same, because it's a diode. Therefore, there will be also leakage current due to when it's off, there's still some reverse current, or we call it the current when it's the current at very low amount. Okay, so now ideally nothing. So let's say if you apply here, okay, now I make a back-to-back, and now this is the structure. Now if I apply, try to make your life more, I want you to understand. So if you connect the source to the ground, and we make the drain positive voltage here, will there be current flowing? Kamalia? Will there be current flowing? Tak dengar.
No,
No, why?
because it is back-to-back diode, so
Yeah,
there will be
okay. So clear, so current cannot flow, even though if you apply a positive voltage there. Now what happens is I apply a positive voltage at the gate. So siapa beritahu saya, Faris ke siapa ke, Rahimi beritahu tadi, what happens is you will repel the hole and you attract the magnetic carrier to the surface here. So what happens is dia akan jadi macam ni. So when you attracted enough free electrons or free carrier to the surface over here, so you can see here, this one is the source, this is the drain. Source are made of N. What are the majority carrier in N time?
Electron.
Okay, so the majority carrier is electron, over here electron. But you can see here at the surface here, now because of this field effect that happens, it changes this region from become P to N. Okay, because the majority carriers that here become N. So I can sort of draw, it becomes like this. So it becomes like a bridge that connecting the source and the drain. So although we have a diode over here, but still we have like a wire connecting the source and the drain. So now if I apply a positive voltage here, I apply a positive voltage at the drain, positive voltage at the gate, I ground the source. Will there be current flowing? Ahmad? Ahmad, you there?
Yes, madam.
Hmm. Would there be current flowing?
Yeah.
Hmm? Yes or no?
I would say yes,
How?
because the gate and the voltage source.
So where does the current flow from where to where? How about the free carriers flow from where to where?
The electrons.
Hmm? Hmm? Who
But
wants to help me? Huh?
is it correct though? Is there current flowing, right?
Yes. How? Anybody wants to help Ahmad? Mhm.
Because it's as if there's no PN junction. It's just one N-type material at the top,
So where's the carrier flowing from where to where now?
from drain to source. No, wait, sorry. From source to drain, isn't it? Current and electron flows to opposite directions.
How about the electrons? Where does it move from where to where? That's not
From
the current
source to
flows.
drain. From source to drain.
Why?
Because the electrons are attracted to the positive current.
To the what?
To the positive side in V, in the drain.
To positive voltage, right?
Yeah, the positive, yeah.
So yes, good. So yes, the answer is there will be current. How? Current is, what is current? Current is net flow of carriers per unit time. So is there a flow now? Yes, there's a flow now. The electron will flow from the source here and go to the drain and go outside and becomes a loop. So you have current. And the current is due to which carrier?
Electron.
Does a hole contribute to the current there?
No.
No. That's why Mosfet is called what do you call it? It's what's the word? Monopolar device. It's only one type of carriers contributes. That's why if you still remember in your first year electronics, can you still remember the equation for BJT and Mosfet? The equation for Mosfet, the current for Mosfet is much simpler because of this, because it's only one type of carrier. For BJT, you need to calculate of both of the electron hole. So when we talk about BJT, how it works, we say electron, BJT, we say electron flowing from emitter to the base, recombine, and then being collected at the collector. In the same time, hole also move, which normally we don't say it, but at the same time, the hole also move, the hole also diffuse from the opposite direction of the electron. Okay, so for BJT, both are happening. Electron move, hole also move. That's how even in a PN junction, you know how it works, right? Electron hole moves. But in MOSFET, because of the structure and the physics of it, it's only one type of carriers contributing, which is in this type, and this is called NPN, or the NPN, NPN, or sometimes called N-channel MOSFET. N-channel MOSFET because the channel, this bridge is called a channel, and it's N channel because it consists of electrons. So that's why it's called N-channel MOSFET, because the channel here are made from electrons. So it becomes one continuous. So the condition for current to flow in a MOSFET, you must have this channel. This channel must be formed first. If there's no channel, there's no way current will flow because of the back-to-back diode. So I can draw the diode like this as well here, if I want. So it's everywhere. If I want to draw, kita boleh draw macam ni. Yeah. Because every time there's a P and N meets, you have a diode at this junction, at this where the P and N meets. Okay, so if there's no channel, there's no current. So number one is to create the channel, and how we create the channel through the field effect. Mechanism. So that's why you call field effect transistor. Okay. So now we understand how we get current. Okay, next question. Let's go to the next step. Any question up to here? I'll go to the next one. Yeah.
Is there any chance of electron and hole recombine at P?
Electron hole recombine at P. Electron hole recombine at P. You mean at the channel?
Yes.
Good question. I want you to think about it. Is it possible? I will not ask you a question if you cannot think. So you need. So his question is it possible to have the combination of electron hole over here when we apply a positive voltage? Possible or not possible? Who wants to answer? Or I might want to answer yourself. I will not ask you a question if I know you cannot answer. I know you can answer. Only if you think. Faris, you want to answer?
I think no.
Why no?
Because hole repel.
Good, very good. So because there's no hole anymore at that region, hole already repelled away. So how they going to recombine at the channel? No recombination. Okay. Okay, Iman.
Okay.
Any more question? No? Okay, let's move. What's the time now? 9:40, 10 minit. Okay. Next is let's talk about so now we understand how it goes. So now what if now I increase the voltage here to become plus positive? So I increase the voltage at the gate. What will happen to the carriers in the semiconductor? Hannah?
Can you say that question again?
I increase the voltage at the gate here. So what happens to the carriers in the semiconductor? If comparing previously only positive one, let's say this one is 5 volt, now I make it 10 volt. I double the voltage.
Would there be even more minority carriers at the top?
Good. So what happens is more minority carrier will be attracted. So if I'm going to draw, maybe now it becomes maybe 2 level. The channel will be thicker. Okay, the channel will be thicker. So now my next question is, how does this affect the current? Will this change the current? I see. Okay, previously, so we have gate, and then you have the, so previously, if this is the case, the electron flowing from here to here, so the current must be going downwards. It's the opposite direction, right? So this is ID, drain current. So, and then you know, right? ID equals to IS. When you're first here, you just memorize ID equals to IS. Now you know why ID equals to IS, because it's just the same current flowing. Okay, now my question is, I increase the voltage here. Does this affect my ID or no? My drain current. My Sarah.
I think the ID will increase.
Why?
Same goes with IS because the number of electron increase.
Okay, good. So the answer is this is like this channel is like a bridge. If you drive a car, right? If you drive a car and the bridge is bigger, the lane is bigger, 2 lane compared to 1 lane. Per unit time, more car can flow, right? Yes, if you have 2 lane compared to 1 lane. So the same goes here. When you make it bigger, the lane is bigger. Therefore, per unit time, there are more carriers per unit time that can flow from the source to the drain. So that's why ID will increase. So if you increase VG, this is VG, yeah. If you increase VG, ID will increase. Why? Because the channel becomes thicker or bigger in terms of thicker going downwards. Good. Now let's say the next condition. Let's say I make the VG now remain constant at double here. Mungkin lagi senang I go to the first condition again. Saya make the gate voltage 5 volt again, just plus, just not double. So I have this channel over here, but now I double the VD, the drain voltage. I double the drain voltage over here, plus. I double the drain voltage. What happens to the current ID? So I double the drain voltage. What happens to the drain current? Elmi? Elmi?
I think the drain current will stay the same.
Why?
Because the channel is same.
So you change the voltage of the drain, doesn't change the current, because you are saying the channel remain the same. The size of the channel must remain the same. Do you agree with this, Ikram?
I think it's effect.
Huh? You disagree with him?
Yes.
So what do you think? Huh?
Um, I don't know, but I think it is wrong because
Untuk perasaan ke apa? Huh?
um, um, I don't know.
Okay, so kadang-kadang kita engineer mengikut perasaan dan hati juga. So tanya orang lain pula lah. Faris, what do you think? Faris?
Because of the channel is same thickness. So the current
So you agree with Elmi? Tak dengar.
Increase the drain voltage.
Yeah, I increase the drain. I double the drain voltage now.
Maybe the electron will even the thickness of the channel same, but the flow of electron more compared to the
How?
flow.
How? Huh?
The flow faster.
Good. The answer is because current is rate of flow of current, flow of free carriers per unit time. Dia ada per unit time. So yang tadi channel bigger, dia per unit time because you have more carriers can flow. Okay, when we increase the voltage over here, it means that we increase the rate of attraction of the electrons to go over there. It goes faster. It goes faster. So if you increase the drain voltage, the answer is the drain current will increase if you have this channel, because the is the attraction, the carrier, the electron will move faster. In Mosfet, normally the analogy I will say the electrons are like cars. Tadi saya cerita pasal kereta and cars. So you are driving in a like one lane become 2 lane, then you can have more per unit time carriers going through. The other thing is carriers was like a car. The drain voltage is like the gas that you tekan tu, apa benda nama dia, tekan gas tau, panggil apa? Apa benda bahasa Melayu? Tekan minyak. So if you put more on the pedal of the kat minyak tu, dia kereta akan pergi laju lagi. So macam itulah dia punya konsep. So therefore more per unit time carriers will flow. So therefore you can increase the current due to two things. Number one, you can increase due to the VG, the gate voltage, and another thing you can increase by increasing the drain voltage. And normally the source will always ground or we make it negative. Biasa ground je lah for reference point. Okay, so what's the time now? Berapa dah ni? 9:50. Okay, good. So I think next class we'll continue with P channel Mosfet. So this is N channel Mosfet. So we should know about P channel Mosfet, and after that we'll talk about the three in Mosfet. In BJT you have cut off, saturation, and forward active, right? For BJT. For Mosfet, what do you have? You have cut off, you have saturation, and you have linear mode. You have linear, saturation, and cut off. So next class we'll be learning what happens in cut off, what happens in linear mode and what happens in saturation mode. Okay, to the physics. So in your first year, you just know, you just hafal lah. Now you understand why is it become like that. Okay, I think that's all for today. Any question before we end? No, you all understand? Okay. But for Mosfet, normally I don't cover the secondary effect of Mosfet. And also I don't cover how the energy band diagram for a Mosfet. The reason being because it's a bit complicated, susah. So if you can just understand through the structure, the one that I explained just now, is enough. So we go through that, we'll learn how the linear cut off the saturation mode, and we finish. So only sikit je lah I will cover Mosfet. Okay, we won't cover secondary and won't cover energy band diagram. So energy band diagram dia ada insulator. So dia jadi complicated sikit. The physics of it. Alright, so can we have a doa please? Next week we'll have class. In the final class, can you remind me to give some tips for your exam? If you don't remind me, I won't give you lah.
But the password for today, I forgot to ask.
Password for today is Mosfet lah.
Mosfet, yeah.
Okay, waiting for the honor. Although your final exam will be open book, but still I think always students say not enough time. Sebab ni awak nak baca, nak jawab pada masa nak cari Google. So my advice for you final exam, you need to time yourself very wisely, because suddenly you realize 1 hour gone like that, and suddenly many students last minute say, oh, they don't answer there may be 3 questions only, they don't answer the final one, finish 1/3 gone, because they don't manage their time properly in the exam, because you terlalu carried by, because you open book or you can Google already, you don't realize only 1 hour. So don't do that mistake. Okay, doa. Or you love this class too much, you don't want to go out. Yes, Faris.
Bismillahirrahmanirrahim. Alhamdulillahirrahmanirrahim. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma inna nas'aluka salamata fid din wa 'afiyata fil jasad wa ziyadatan fil ilm wa barakatan fil rizq wa tawbatan qabla al-maut wa rahmatan min al-maut wa barakatan ba'da al-maut. Allahumma inna fi sakaratil maut wa najat min an-nar wa taqina as-sab. ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار. صلى الله على سيدنا محمد وعلى آله وصحبه وسلم والحمد لله رب العالمين.
Alhamdulillah rabbil alamin. All right, thank you very much. Let's end the class today with tasbih kifarah and surah al-Aqs. Subhanakallahumma wa bihamdika nashhadu an la ilaha illa anta nastaghfiruka wa natubu ilaik. Bismillahirrahmanirrahim. Wal 'asr. Innal insana lafi khusr illa alladhina amanu wa 'amilus solihat wa tawasaw bil haqq wa tawasaw bis sabr. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you.
Yeah.